right, class, we are now on chapter 5.6 and 5.7. This is naming compounds. All right, so chemists, we have developed a way to name compounds, and knowing how to name these compounds helps you understand the chemical formula and vice versa. So if you know the chemical formula, you should know how to say it, and if you see the name, you should know how to write the chemical formula. So many compounds also have common names. So we're going to cover the common names first. So H2O is water. We don't ever use dihydrogen monoxide. We use water. Some of them are just so familiar that the common name overrides everything else. And there's not really, and so we don't use a systematic name. There's a few others, but as they come up, if they come up, then I'll tell you. And there's no system to them. So that's why we're addressing this. I'm never going to give you dihydrogen monoxide and ask you what it is. It's water. That's fine. Okay, so naming ionic compounds. The first thing you need to do when naming a compound is identify it as one. So you need to know, are you looking at a molecular compound or are you looking at an ionic compound? This is the first step to stop you from making mistakes. Students, try to force the naming of the system that is easier for them on ionic and molecular compounds. You need to stop right now and tell yourself the naming system is different for both. And they're drastically different. They're not drastically different, but they're different enough that you'd get it wrong. So first thing, are you looking at a molecular compound or ionic? Then you need to use a system that goes with that compound. Right now we're looking at ionic. So anytime you have a metal and a non-metal, that is an ionic. And we have two different types. We have ionic compounds that, with the metal, that only forms one type of ion. So it only has one type of charge. Those are main group ions. That's with the A. And then we have metals that form different type of charges for that same element. And that's transition. Those are with the B. And they have two different naming systems even within this system. Okay, so the first type, type 1, contains a metal with an invariant charge. Very fancy word for the charge doesn't change. So anything that's group 1 is going to lose that 1 electron. Anything group 2 is going to lose 2 electrons and so forth. The second type is called type 2, contains a metal with a charge that can differ in different compounds, different oxidation states. So something like iron has an iron 2 and iron 3 oxidation states. And you don't know which one you're dealing with till you actually do look into it more. Some metals are usually but not always found in transition metals. So some of these actually start overlining over to that little staircase that have variable metals in it. I've given you there's some periodic table in my slides that have shown you the charges on some of those. Some transition metals such as zinc and silver only form one charge. So they're very similar to group 1 and group 2. Zinc will only lose 2 electrons, silver only loses 1. That's it. Some main group metals such as lead, so Pb is lead and Sn is tin, form more than one type of cation. So you can see we have tin 2 and tin 4. And over here we have lead 2 and lead 4. This is what it means by different oxidation states, and I spelled oxidation wrong. Okay, so I don't like this chart. I think the way that they have named this is, they make it harder than it needs to be. So right above it, it says metals whose charge is invariant. And right next to it I put in parentheses, charge doesn't change. So this is a map of charges that don't change. So here is the transition metals. So some of these actually right here still are part of the transition metals, even though they're under the group numbers here. They have different oxidation states. And then here, the ones in blue are showing you the ones that stay. Now we're only looking at metals. This is not for non-metals. So here you can see the different blues show you the oxidation states that do not change for these. All right, so now we're going to get into naming. So if we look here, we have chromium. Chromium has 2 different oxidation states. This is just an example of some. The name of it is, there's no space. So you see all of these have parentheses and Roman numerals. This is the newer way of naming. This is the older way of naming. And let me explain the newer way. I'm not going to talk about the older way because we don't do that anymore really. Some instructors still teach it, but I don't. Chromium 2. So you put a 2 in parentheses in Roman numeral. Chromium 3, put a parentheses, no space, in this. Iron 2, same thing. Iron 3, same thing. Cobalt 2, same thing. Cobalt 3, same thing. Copper 1, just a plus sign with a 1. Copper 2, 2. So if there's a 1, you have to write a 1. You can't just leave it without the 1. It has to be there. tin 2, tin 4. If you don't know the Roman numerals, I have them coming up. Don't panic. Mercury 1. This is a little weird one because there's a 2 down here and a 2 up here. I usually try to avoid mercury on it, to be honest with you, because of how confusing it is. Lead 2, lead 4. Now, the lower oxidation state goes with the OUS. The higher oxidation state is IC. So with the older naming, you would say chromis, and you would have to know that's a 2. And with chromic, you would have to know that's a 3. With iron, ferrous 2, ferric 3, cobaltus, sounds weird, 2, cobaltic 3. I don't name these this way. I use these. So I'm showing you because they're on the slide, but honestly, I don't use them. It's going to be naming with the Roman numerals. Okay, so let's go on. All right, binary. Binary means 2. So binary compounds are those that contain only 2 different elements. So you're talking about a metal and a nonmetal. The names for binary ionic compounds contain a metal that forms only one type of charge and has the following name. So how we're going to name this is you name the metal. Just name it sodium. That's it, sodium. Now the base is different. The base changes. Since the charge of the metal is always the same, and it's not specified. So we don't ever bring up the charge in the name. So sodium, it's one of those fun things again. You need to know it's a +1. And with the anion, the base, we take chlorine, and we take the last syllable off and change it to "ide," so that INE, that "ine," is gone and is now "ide." That means it's changed into something else. A reaction has been done, some kind of action has been done on it. So it's not chlorine anymore, it's chloride. So put those together, sodium chloride. And that's the naming for all of these. So let's take a look at the anion. We have fluorine, we drop the ending, it's fluoride, chlorine, chloride, bromine, bromide, iodine, iodide, oxygen. Now this is a weird one because we don't just drop the last, we lost the last 2 syllables. It's oxide, drop the Y. So you see it's just ox. Sulfur, sulfide, and this shows you the base name. And nitrogen, nitride. So this is a good table, and you should understand this table. Showing you the ion, it's just giving you the base name, and it's showing you the name after it's going to be joined. These are things you have to know with the vice versa. Remember I said if you look at the name, you should know how to put the chemical formula together. And if you look at the chemical formula, you should know how to put the name. So this is definitely a slide I would save and look at to study. Binary ionic compounds with metals whose charge may vary. Now this is where the Roman numerals come in. And so since the charge of the metal and the cation is not always the same, the charge has to be specified. So when we write this out, we have to specify the name, the charge on it, or we just don't know what we're dealing with, because copper could be copper 1 or copper 2. So in this case, we're dealing with, we specify with the Roman numeral, in parentheses, and no space between the metal and the Roman numeral, because that Roman numeral signifies the oxidation state, and that is with the metal and not with the non-metal. So in this case, that plus means 1, so we would write copper parentheses 1. There's 2 for an oxidation state, so it's copper 2. That would be the oxidation state. Okay. Now transition metals, zinc, cadmium, and silver have only one oxidation state. So we don't actually have to use Roman numerals for those. Those are fine. Zinc chloride, cadmium chloride, silver chloride. We don't use zinc 2 chloride. But if it has more than one oxidation state, you absolutely have to. So in this case, we have copper 2, copper 1, iron 2, iron 3, lead 2, lead 4, chromium 2, chromium 3, parentheses always. And sometimes you might not see it, but how you're supposed to learn it, parentheses and no space. Definitely no space, because it goes with that element, that metal, and not without it. So if you write it without it, it would be wrong. I would mark it wrong. And then here I'm giving you from my other class some charges that it's shown in that book, so you can see some of these to help you understand. All right, the full names for these type of compounds have the following. Name of the cation, so we just name the metal. There's nothing more to do here. You just name the metal, very easy. Charge of that metal. So the Roman numeral, so this is for metals that have a different charge. And then base name. Everything with the base of an anion, drop it at the ending, last syllable, and "ide." Okay, so we can determine the charge of the metal from the chemical formula. The sum of all the charges must be 0. So remember when I solved for X? You can do this with all of these, even with the ones that have various charges. You can still solve because you'll always know at least enough information of the other element to be able to solve it. So the charge of ion in iron 3 chloride must be 3 for the compound to be charge neutral with the 3 chlorides. Why? Because if this has 3 and in each one is a -1 charge, this is -3. So this must be 3. But here's the other thing that this isn't telling you. You're crisscrossing. Remember you crisscross still? So this is iron 3 chloride because this 3 went with the oxidation state of iron. Name the compound. So in order to name this is iron 3 chlor, drop the ending "ide." Iron 3 chloride, and that's what it looks like. Iron 3 chloride. So in this case, we are given a compound, but we don't know how to name this. So you could do the fast way that I told you, which is just remember these crisscross. So this is iron 2 chloride, or you could do the math with it. This is a -1 and it has 2, so that's -2. So this must be +2 because this overall is a has to equal 0. But how do we name it? So we know that this is iron. We know it's iron 2. We've already figured that out. And now you do chloride. So the iron 2, no space, chloride. These may seem difficult, but the rules don't change. It's the same format over and over for these variable metal charges. And here is some more information to help you understand. And I've given you the Roman numerals right there because even I sometimes don't remember them. Okay, so let's name this. Name the following ionic compound containing a variable metal. So we have SnO2. So we have an oxide there. So let's take a look at what we have. We have a metal, which is tin. I think this is in Latin. That's why it doesn't match up with what we understand it to be. So we have tin. It's a transition element. So that means it's not silver or cadmium or zinc. So it must have different oxidation states. We have a nonmetal, which is oxygen, and it is an oxide with a 2-. So we basically solve for X, set this up with them summing up to each other. So here we have X, which stands for Sn. Here is our information for our oxide. We have 2 of them. That's the 2 here. And it's a -2 charge. And make it equal to 0. Now, do the math on here. So this ends up being X minus 4 equals 0. Bring the X over. The metal charge on this is +4. So this would actually be tin 4 oxide. Yes, it doesn't look like that. That's because if now, let me break this down. I should have brought this up. If this is an S +4 and this is a 2-, crisscross them down, and that means you have an S2 with a 4. You can reduce down, and that's what's being reduced down. So that's the bad side of being reduced. You don't know what the actual oxide is unless you know how to do this. These are one of these fun things that are implied, and everybody's expected to know. All right, so we have the 4, so there's our tin 4, and then we bring it together without a parentheses, without a space. So it's tin 4 oxide, but that's what tin 4 oxide looks like because it's been reduced down. Why is calcium oxide not calcium 2 oxide? That's because calcium forms one type of ion, only one oxidation state, one charge state. Therefore, the charge of the ion is not included in the name because it's always a 2+. When we use Roman numerals, it's for the metals that have more than one oxidation state. So calcium is in group 2, so it loses 2 electrons. Okay, so now about naming with ionic compounds with polyatomic ions. So we have nitrate here. So how do we name these? Very simple. Just put them together. Potassium, the metal, the metal's always the same. We don't change the metal. Potassium, that's it. Nitrate is a polyatomic ion. We just say it. Potassium nitrate. And you should be able to write that out and pull that out, vice versa. So now we're given iron 2 hydroxide. Why? Because I'm looking at the crisscross of how to say that. So that's telling me that this iron has 2+. So I'm going to write out the 2. iron 2 hydroxide, because that 2 is going to go here. This is a -1, which puts a 1 here. If a compound contains both polyatomic cation and polyatomic anion, use the name for both. Ammonium nitrate. This is a plus 1 right here. So this is a 1 and a 1, so that's why you don't see anything more with this one. All right, naming ionic compounds with oxo anions. This is oxygens. Many oxygens is what this means. So many polyatomic ions have a lot of oxygens. And by naming them tells you how many it has. When series of oxo anions contain different number of oxygens, they are named systematically according to the number of oxygens in the ion. If there are 2 ions in the series, the one with more oxygen atoms is given the ate ending, and the one with fewer is ite. So here's a perfect example of nitrate. If you hear trate, since you've memorized these polyatomic ions, you know that's NO3. And if you hear nitrite, that's less oxygens, that's NO2 minus. Sulfate has the most, so it's SO4 2 minus, and sulfite is SO3 2 minus. Here are more. They don't go away. If there are more than 2 ions, then the prefix is hypo, which means less, and per, more than are used. So hypochlorite. Now, one thing I want you to look at, the charges don't change for these. None of the charges change. The only thing that's changing is the amount of oxygens on those compounds. So hypo means 1 oxygen, hypochlorite. Chlorite is 2 oxygens. Chlorate is 3, and perchlorate is 4. So make sure you say the word ion on all these. Hypobromite is 1. Hypoiodite is 1. Bromite is 2. Iodite is 2. Bromate is 3. Iodate is 3. And perbromate is 4. And I never say this right, periodate is 4.